All right, let's get started. So, in the next hour or 15 minutes, we'll explore why UPLC performance matters. We'll see some real-world impact examples, and then we'll get hands-on with the framework. And by the end, you will understand how to use it, how to contribute. You can contribute benchmark, you can contribute submissions to those benchmark, and together we can make it better. So, sorry. Yeah, that's the structure that I already told you. And before we start, please use this repository, clone it, and then just do nix develop. It will start building the shell. You can enter it and let it stay for now like that. Or if it's done building, you can follow me, maybe by trying some simple commands if you want. Okay? So while this will be initializing, let me explain why we are focusing on the UPLC performance today. And it all comes down to one fundamental principle that makes Cardano and programs on Cardano different from traditional computing environments. It's like, and why every optimization that you make has a massive impact. And imagine that you deployed a smart contract on Cardano. Every time someone uses it, it's 3,000 plus validator nodes that execute your code. That's already different from a classic, like a single computer evaluation. And this is a distributed computation, so that's a good mental model for UPLC. It's decentralized, and this makes optimization critical. Why? Because in a decentralized network, we cannot solve performance problem by adding more servers, or in this case, we cannot solve it by adding more powerful servers too. We don't control them. So let's see what it means for costs. Unlike traditional software where one, as I said, inefficiency is affecting only one computer, here each inefficiency affects thousands of validator nodes simultaneously. And this formula shows that, the phi formula that you can see, it shows that both memory and the CPU steps that contribute towards the final phi. So we need to optimize those for sure. And they matter, and they have weights associated with them. That's called the cost model. And every node will pay this cost. So let's see how it looks like in practice. In practice, real transaction cost. So if you have a simple transaction that just transfers the value without scripts, it's approximate in that region of 164 ADA. But if we have scripts, then it's the costs of running that transaction rises because it's associated with the script. And what impact can optimization have on these costs? Typical optimization gains, you can see 60 to 40% of a cost reduction. This is realistic and not purely theoretical. So these economics are compelling. You will be doing this because there are money behind that. We can have a more detailed mean swap example. We have if we have approximately 1 million transactions per year, where you have 2 cents or 200 of ADA savings, altogether that's $24K annually. It's just something that's worth considering. So developer return of investment is 1-2 weeks of optimization work. You can have 400-900% of a reduction in the first year. Why not to do this? There is also a hard ceiling on how much you can execute. So in terms of the memory units, those affect phi. In terms of the CPU steps associated with the phi, and the script size also associated with the phi. So all compiled outputs must fit this bounds for the size, and the all executions should fit the execution budget. And these are not soft warnings, they're hard protocol limits. And they exist to protect the network, to prevent attacks, denial of service attacks, and they constrain what you can build. And Adam knows that. He tried to deploy and it felt constrained.
Yes, it was constrained.
Yeah, so Adam knows what happens when you reach the limits. And
transaction into many.
yeah, so what happens is that transaction fails, if you're stupid, you lose your collateral, there is no partial evaluation, so nothing good happened. So with all that, we can already say that optimization isn't optional, it's required for execution. And these are takeaways that I thought worth a dedicated slide. So if you only remember 2 points, then it's better be these 2 points, that optimization isn't optional, and language compiler that you choose, since it also comes with a certain set of optimizations within, it's also, the choice matters. So we want to benchmark, we want to make our decisions based on the data. And if we would to benchmark this, then we'll face the challenges. We need to do it right. So in this context, right means we get exact same results regardless of who runs it, when it's run, or where. It's critical for trust. A second point, we want to have a source code transparency, because if we have a black box benchmarks, even if it's that fast, it's kind of beyond, doesn't meet the goal. We want people to see, here is this source, here is how it compiles, and this is why it performs this way. And that will be a building block in the mental model of a developer. They will know, like, for example, Skylar was saying here that iteration is costly, or recursion is expensive. That's the bit of your mental model that you can really see by looking at the source and by comparing it with the UPLC. Some other technical challenges are that some validators, they have multiple transactions interacting with them. They're like whole protocols, so we need to manage state properly, and we need to abstract from the off-chain part, because that's like out of the scope of this problem. So if we want to compare compilers, then we want this comparison to be fair. Like, we want to compare apples with apples. That's a challenge. We want to present results in a nice way, and we want to make it open for contributions for it to grow. And so here comes the CAPE as a solution to this like really big problem that I outlined. It's not a problem. So what is CAPE? To your question, it's a comparative artifact performance evaluation, and I thought about that. So it's not just like a random word generator. Comparative, it means that we can understand the thing when we put it in a correspondence with other things like this. Artifact, here I mean like something that your compiler produces, right? So it's a UPLC program. Performance, this is an interesting one. When we say performance, we don't mean performance like a walk log time, it runs fast. We mean broadly effectiveness. And I will be expanding on that later. So it's not a walk log time. So CAPE is comparative artifact performance evaluation. But then ChatGPT said, no, I don't agree with you. It's not that. It's actually a Cardano application performance evaluation. So, okay, let it be. How about I put it on the slide and we're good? Okay. So this is the framework, the benchmark developed by the Pluto Score team at IOG. Yeah, and it is meant to be unbiased, fair field of play for all compilers. So no favoritism, just objective measurements. And this is why also transparency matters. We focus on writing code. So the authors or the users of this framework, they can focus on the writing code and not really like the measurement infrastructure of it, because the framework does it for you. So there is this CAPE tool, command line tool, and it will, given your UPLC, it will do the rest, which is nice. So you can focus on producing the UPLC. Right. It uses same environment as mainnet node, the latest one uses. That means a certain version of the CK interpreter. That means the specific cost model that's deployed on the mainnet. Right, and this way we can connect it to the real world, so something that's running, right? Initial version didn't follow this constraint, so I had a newer version that people, because it was all transparent and people saw sources, both of the Plint source and the UPLC, and they say, oh, this is the feature that is not deployed yet on the mainnet. It's unfair to use it, so I immediately downgraded it to be fair. But I hope later on everybody will use that feature. Accidentally, it was casing on built-in constant, something that Roman is telling right now. So what's included? Scenarios, different benchmarking problems, tooling, and visualization means. So you will see the results visually and analytically too. It's open, as I said, community-driven. So if you want to contribute a benchmark, if you think that that benchmark is wrong, we need to do it better, open. Pull request and done. Yeah, now let's talk about who benefits from it. And I see that different user personas or different roles can benefit from it differently. So this is why I felt like it's important to dissect. Compiler authors, like classical, or not a classical, the best example would be the Skylar, who was telling about his compiler, J to UPLC, like 2 hours ago here. And I invite him to participate in a bunch of claims that he made about the performance of that compiler could be really put onto the graph, could be put into correspondence with others, and I think this makes them way more substantial and backed by the data. So the compiler authors can showcase and improve and see and kind of learn the ideas from others. Okay, DApp application developers, how they benefit. First of all, they see the repository of battle-tested validator patterns, or not only validated, but just patterns of this is how you use UPLC or compile to UPLC in a way that's really like winning the competition, if you will, or the most performant way. And it could be done by the compiler engineer, and then the app user just look, okay, we need to do the loop unrolling because that's what brings the benefit. And the new developers, they can make informed decision when they're committing to a certain tech stack. Like, should I use Scalus? For sure. I woke up, Alex. Or should I use Plint? All right. So to show you core entities visually, maybe that's the best way to remember that, memorize that. So the core entities are the scenario, or in other words, benchmark. So it's kind of problem that you need to implement, and then it will, your implementation will be measured. So it contains the problem definition, it contains the test suite, because it's important to measure performance of the correct thing. So you need to first establish to some level that it is correct, because otherwise, I mean, we can really, because it's transparent, we can say that if it's incorrect, then people will see it in the source code, but maybe not. So This is not like a testing framework, it's not the focus of it, but some correctness verification is there in terms of the test and expected behavior. And example would be of such a scenario could be Fibonacci naive recursion. I will tell later about the naive recursion part. But and then one scenario can have many submissions associated with that. So different people at different time will submit, and their submissions will include the source code for transparency, the metadata so that we know who they are, how to talk to them, how to compile, how to build it, and then like different stuff, like what version of compiler they use, what operation systems, what flags. And yeah, and this is all packaged in a folder, and you can see that the folder contains the compiler name, compiler version, the GitHub handle of a person, and maybe some optional part, like I was optimizing for execution budget here, for example. And then the workflow becomes first somebody makes a scenario, like a Fibonacci naive recursion, then other person, or maybe the same person, makes a submission, like, okay, I have a Fibonacci implemented in Plint or Aiken, and then the CAPE measures that, and then it's all published, and then it's all on report. Very simple and powerful. I do have a bunch of slides that go into the details about that, but since in the interest of time, I will quickly skip them. If you will want this as a cheat sheet for your hands-on part, I can give an URL later, and it's there. And then we'll see the report published here. Let me open it, because one picture is worth 1,000 words, and that's the report. By the way, the CAPE is resting on the Plint here. And we don't have many submissions yet, but this is just the beginning, and it was ramping up pretty rapidly. These are the initial, like the first Zoom level data, but if we want to go deeper, let's say we want to see how different compilers score on the Fibonacci benchmark, then we can see that, let me do it this way. We can already see this is the first two, they are actually the same byte to byte. They are the same to UPLC. Like you take different, completely different looking like a source code, completely different compilers. Compile them down, you get exactly the same UPLC because it's optimal for this case. And this is what Plutarch and Scalus already achieve. And at this point, people can think, oh, we take those, and they can go and see the source code, like what would it take in Scalus, for example, to achieve this optimality, or as compared with what would it take in Plutarch. And then other submissions are catching up, so it's not, when they see like, okay, there is something here, they resubmit, they improve, and it's like moving. Maybe later on we'll do this, you know, like animation where like year 2300 and like somebody goes first. All right, back to the presentation.
But if someone like submits a new like comparison on the same algorithm, it replaces the previous one, or
the short answer, it depends.
okay.
But probably yes, could be. Let's go make it full screen. All right. Now I need my cursor back. Now let's talk about metrics. First, I need to regain my cursor. Yeah. So what are we measuring? And at a high level, I call them raw metrics and derived metrics. And by the way, derived metrics idea came from Alex. So raw metrics, what do we mean? We mean something that we can observe by running that program on the CK machine, and we directly get this data. You all know that there is the execution budget, you know that there is the CPU units and memory units, these are raw. On top of that, we have as a raw matrix, yeah, there is the whole slide about that. Oops. Yeah, so the script size is another one important, and you can look at it from different perspectives. There are several ways of measuring it. Probably the best way is to measure it by looking at the flat CBOR encoding the same way we have it on the mainnet. Then you will just count bits or bytes. That's one way, and another way is you can see how many nodes are in your AST, and that's decoupled from the way you serialize that. This is also a metric. Yeah, let's look at the. No, let me say this. The script size is the property of what? What do you think? It's the property of the artifact, right? Of the program. And the execution budget, is it the property of the artifact? So it's like they are properties of different entities, right? So it's important to have it in your mental model that one script can have multiple execution or evaluations. And we have properties on the script, and we have properties of the evaluation. If it fails in the beginning, that's a very short evaluation. If it goes deep, that's a very expensive one. I don't know. I felt like it's important to underline this difference. And the derived metrics, they are close to the heart of those who own the ADA, because they will be paying for that. It's like, for example, like transaction fees are paid with ADA, and we can measure, or we can say that if you have this script, then it will mean that in terms of the transaction fee, we are talking about this number, like 1.5 ADA, which is something that way easier to understand than like what is the 15 million of CPU units, who knows, right? So that's why, and we are not measuring them directly. So budget utilization is like what percentage of the whole transaction budget this script will fill in, or okay, maybe not, if not this transaction, that what is the percentage of the block that this script will fill in. And the same thing, but from a different angle, it's like, okay, how many such scripts can we feed into the single transactions? Oh, right, I had a slide for it. So the source code is a property of program, etc. Now, when we are talking about more complex programs, they are interacted with multiple times. Let's say we're talking some validators like two-party escrow, or you have to deposit thing, you have to get it. So, and each interaction is the evaluation of the validator. So, and each one costs money. We want to measure all of them, and we want to aggregate these measurements into something unified. And so there are different strategies. The CAPE framework will measure all of that. It will apply these strategies. So you can choose which one you want, but for the report, there are some strategies that make more sense and they are already chosen for you. Yep. So very often, optimizations involve trade-offs. Like sometimes you can optimize the execution budget, or you want it to be as small as possible, but that inevitably means that you sacrifice the script size. For example, memoization can have that effect, right? I thought it's important for authors to show what they were optimizing towards, and maybe submit several alternative implementations saying, if you need to optimize execution budget, then this is the thing, and if you need to optimize the script size, then this is, and they will be in a trade-off relationship. And by using this variance, you can indicate that. Or you can, it's just a like alphanumeric string. You can say something else. Like people who already submit something, they use prepack as an indication that this particular submission uses prepacking answers into the byte string or something like that. Okay, now a little bit about the benchmarks. Maybe this is a confusing slide. Let me jump and say there are multiple dimensions. And one of them is, I call it isolation, maybe for the lack of a better term. So we can test or measure the program in isolation from ledger, Bluetooth ledger API, built-in data. We can just have it really like a factorial, isolated from the ledger, right? Nothing to do with that. Or we can, on the other hand, we can assemble it like here is the script context, here is the decoding phase, and here is the error handling, and then I see it more like an integration, like end-to-end measurement. And that's for the, on one side in this dimension there is this fixed algorithms test and submission where it's made for mainly for benefits of a compiler authors, because this way they can compare apples with apples. They compete with their compilers only. Like you have what you have in the compiler because the algorithm itself is fixed. You cannot be more clever in it. And among the existing submissions, they all have this naive recursion name, suffix, because that means that it's naive. Don't even try to be smarter than that. It's by design naive. Then an open algorithm, and they are just called Fibonacci, factorial, or two-party. They demonstrate both compiler and program optimization, end-to-end, as I said. And interesting effect that happens with the open algorithms is that the people or submissions, they collectively discover the optimum, like which algorithm turns out to be the most optimal one. And by the way, for Fibonacci, they discovered that the prepackaged implementation is optimal currently. At least for how that test is made, it turns out to be prepackaged. But it won't scale, so maybe we can have another benchmark that will actually hit the point where the prepackaging strategy fails and you need to find another strategy. Prepackaging, maybe. maybe.
Yeah, you store like a byte string. Yeah, and you cache the results and then you use byte string index.
Yeah.
Anything where you abuse built-ins tends to be way faster than recursive solutions.
Did you invent the name prepackages?
No.
No. All right. And so that was this open fixed, that was the one integration dimension, and another orthogonal dimension is a complexity. And so you can go from the simple simple programs to a complex multi-step validators. And I call simple ones synthetic because they have nothing to do with the real world. They're like not natural for the blockchain. And they have nothing to do with the script context. They are easier to contribute, faster to implement, but they are less representative of the real world usage. And for the hands-on session, I was thinking we can use synthetic because that's simple to start. Now, real world scenarios, they will have to deal with the data encoded inputs. They will have to deal with the script context, with transactions. This is a different story. And both are supported. So the set of benchmarks is growing. I hope you guys also contribute, and maybe even on this workshop. So what it takes to create a submission, scenario. Submission. In this case, we understand the scenario. So because there are rules of the game, what is expected, like written in the human language. Like for example, here, this is the fixed algorithm scenario. It's meant for compilers. This is what you meant to implement in an informal way. And then CAPE tests, it's the set of tests, describe it in a JSON DSL, that is more formal or machine checkable way of saying what you expect. Right, and maybe a few words about the edge cases, like how to work with negative numbers for Fibonacci, for example. Then you can create a submission project. The idea here is that by saying project, I mean a complete thing that you can open, that you can git clone, build it, get your artifact, and that's ready to be submitted. So it's reproducible or workable. You can fork it and modify. Then, but you keep it separate and you keep it public, and then you build your stuff. Then you remember this immutable reference, the git hash, and then you simply refer in the source section of a submission. You say, here is the project, here is the exact hash, here's the source file. Go look. If you want to build it there, verify that that's the same thing. That's one way. That's a dedicated public GitHub repo, and I used that a few times already. But then there is another approach, is that you can simply have your project locally and embed it into the SRC folder in the submission itself. It's like a snapshot. No resolution of references, but that's whatever floats your boat. Then you initialize a submission, and you have to say what scenario you're implementing, which compiler, of which version of that compiler, who is implementing it, and which variant is like, or skip the variant completely. Then you fill metadata, that's boring part, and important to include the UPLC file. And extension is UPLC. It's already recognizable by GitHub, syntax highlighters. It's the textual representation of the UPLC program. It's different from how they are represented on the blockchain with the flat and CBOR, but because we need transparency, because we want to eyeball it, and we want to see what's inside, it's better to have it open. Right, and it just matches the scenario name. This is the essence of a submission, just one file. Then you make a PR, and the CI/CD pipeline measures everything, publishes the report, and if you want to iterate, then you can not merge that PR, because every PR also gets its own isolated preview. For the pull request, you have your own dedicated preview report, publish it on GitHub pages. And when you are satisfied, you merge the PR and the global report is updated. A few gotchas is that since maybe that's the first time that text and pretty printed encoding of the UPLC program is used across different compilers, because normally people exchange, as I said, in the flat form, but here it becomes a lingua franca of that framework, and it's important to get to open the spec and see how the names, for example, are declared there. I've noticed that different compilers implement the names differently here. So, for example, you cannot use dollar in the name, but Scala does. Yeah, I don't know. We can talk about that afterwards. Right. Then there is.
Those are not valid library indexes.
Sorry?
Those are not valid library.
Right. Yeah. These are names for humans, and we can afford that because. Yeah.
The reason behind using text UPLC instead of just CBOR hex or flat.
Sorry. Could you repeat the beginning of the question?
What's the reasoning behind having UPLC-CAPE require textual UPLC instead of flat?
A few times it came in handy that we can open the UPLC file and see what's inside. For example, Alex, oh, by the way, here on the source it's less on equal, but this built-in function is actually just less than. Right? That's a mismatch or something like that. So people look at it, people get impression, they verify, they see, maybe the Z combinator is got inlined here this way, and there it's got inlined that way. I mean, there is a limit to how much reasoning you can do this way, but it enables some of it, so I thought it's better.
But if they submit in flat, can't we have like use the Cabal UPLC tool to just get the textual encoding from flat?
Good idea. I will take a note, and that's the feature request for me. Maybe we can, because they are isomorphic, maybe we can...
No?
No?
There's a distinction, because in flat you lose the names, the variable
But they
names.
can be recovered, right? Like ABC.
Yeah. You just,
But sometimes you want to give it meaningful names like,
Yeah.
like my best counter or whatever.
Actually, like you submitted first print, and it was like amazing, like not even close to other submissions. And I was like, why? How? And I just opened the UPLC file, which is handy, and it uses like syntax is not valid. It's not valid UPLC stuff.
they use the features that
They
I'm
use
on main.
a case on constants and stuff like that. So this visibility of UPLC is
It would be really good to have two different leaderboards, one for the current state of research and one for mainnet valid UPLC.
Another one, good one. Is it recorded? So 2 feature requests. So the hands-on part begins. I hope that the Nix shell already works for you guys.
Almost there.
I set up the binary caches specifically for that repository. If you use this cachex.com, and you should simply download everything.
But it's building.
Maybe I should have said that.
Mine is almost there for you. That's all.
That's the usual.
Yeah.
I think you started 30 minutes ago.
Yeah.
Yeah. Okay, and the idea is to create this simple synthetic fixed algorithm of great common divisor and make it as a scenario, and then create a submission. If you don't have enough time to make a submission, still fine. You still learn how to interact with the tooling, but if Nix is
It's done.
done, okay. Now, my idea was that, this is just the detailed description how you create a scenario. So you just initialize it from a bunch of templates. You say just CAPE benchmark new and the name of the benchmark. You get this directory structure created for you. Then you go and edit it, and you will have to create the CAPE test JSON. The format is specified. There is this documentation for that and examples for it. It's not really difficult. You just say, this is the input, this is an expected, like either error or expected result. Input, result. And if you give it enough inputs, enough for people to not try to cheat, maybe some inputs can be big so that I don't know, it's your imagination. Then somebody else can, or maybe you can, one create submission, one creates scenario, other person creates submission, like a game. Then that's an implementation part. It's a few comments too, driven by the templates. So, but what's important that you need to have this UPLC file in the end, like using a compiler of your choice, whatever. Maybe Scalus, because Alex can help with that if you want to learn that, or Plint. Right, I'm ready to support whoever is brave enough to venture into that territory. There is one caveat, or not a caveat, but rather peculiarity. If your Plint is your language of choice, that you have the dev environment set up right into the UPLC-CAPE repository. And simply due to the fact that they come from the same the CK machine comes from Plutus repository, and the Plint comes from the Plutus repository, so it was so easy to just add it, so I couldn't resist. And if you have a Nix shell, then you have a working Plint environment. And there are actually a few submissions that I made, so You don't even need to set up much. You can just fork the Fibonacci executable and change the body, and that's your algorithm. Right.
On an edge case.
Edge case.
Yeah, and AK releases like the version with the hash of the commit as
Mhm.
the version.
All right.
So there's a plus in between, and it's an invalid version.
Yeah, go on.
But I can just remove the
Interesting
the
one.
hash, but it's the end of the commit hash. It may be relevant.
Yeah.
It's still the same version, but it's a different commit. So
So I thought about what makes it how to uniquely identify submission. What makes a primary key of a submission, and it's a composite primary key because there is no natural primary key. So it's unique in terms of the author, compiler, version of that compiler, and maybe the variant. And yeah, so it doesn't make sense for the same author to do several submissions for the same compiler for the same version without any difference, right? So I thought and if you if you say they have a rolling versions or versions with hashes, that makes it a bit difficult to embed into the primary key. So no Akin in the benchmark.
this shell.
Now, let me open something, or let me.
So when you submit something, you submit both the source and the UPLC. And then
Yeah.
you specify the version of the compiler.
Yeah. If you want to implement it, this Euclidean algorithm in Plint, I can show you where you can take where you can get an inspiration in this repository. So we have this Plint submission app on the top level. It contains. You can see that there are already Fibonacci UPLC, factorial, and two-party escrow, more complex one, and they come from this lib folder, and here you can create, let's say, HS file that is ECD-HS. Then in the Cabal file, you can add it as an executable. Where is the Cabal file? At the bottom, I think.
But in that case,
Oh, you don't even need to modify Cabal.
we have to use whatever version you have there.
It's the same version, the 145 that is on the mainnet.
Okay.
So it will produce the code that's compatible with the mainnet, not without new features.
Okay.
All right. And once you have your executable file in the lib, like the factorial one, let's take a look. This is the factorial. The majority of it is the GHC pragmas, but that's how the life is every day of a Plint developer. They are like spells that make your program better.
Most of the cutoff, right?
Yeah, true. But I thought like maybe being a bit more explicit about that is fair. Yeah, and then really the whole implementation of this submission will be like 3 lines for EC. You can Wikipedia it. And this is intentionally made. No, in this case, this is a naive factorial, right? We have a recursive function that calls itself. So I didn't even try to improve it because I didn't have enough time to compete with others. I was improving the framework while others were competing. So do you want to see factorial, the one that wins, right? Okay. So, or Fibonacci, maybe, because there are more submissions here. So let's take a look at the Plutarch. And here you see this variant. So this it wins because it uses a prepackaged strategy. It turns out to be one of the winning strategies. Like the top 3 winners, they're winners with a prepackaged strategy in terms of CPU units, memory units, maybe not always the term size, because already it's a trade-off, right?
So is this the one where you can use any algorithm or?
No, this one is like open for yeah, you actually can use any algorithm in this one.
Can you remember what prepackaged mean again? I know it's how about
Prepackages, you use a byte array to store.
Tabularized, memorialized.
Yeah, you
Like
use
memorized.
results.
Yeah,
Okay.
pre-memorialized.
These are the derived metrics that I told about with this how do you call it? Diagonal
Memorized.
thing.
All the
No.
points from the
We recurse. If it's too big, we recurse to the last known.
Okay, so you could cache some preliminary points.
Prefix,
Okay,
yeah.
okay. So it's optimized, but it's not cheating.
It's not cheating.
Yeah.
But then the very first implementation in Plutarch without that strategy, this is the 4,000% of the transaction budget, so it would never fit. So you can see these guys are already out because they're so ineffective. And yeah, it means
What's the
that
input for that? Where-
25, Fibonacci
It
25.
must be the naive algorithm.
Yeah. So the Fibonacci 25 for the prepackaged is very good, actually. And this is other way around. Like how many scripts this kind of a scripts will fit. So here we see that it's more than it's approaching 10,000. Right. So that's fine. And then we have this performance data as a table, and the yellow means that they're out of the game in terms of they exceed the transaction budget. Those white ones, they are okay. So you can see here the link to source code and the link to UPLC. This is why we need it readable. Let's start from backwards from UPLC. So, I should have checked that.
Yeah, you just gotta click back.
Oh wait, it's the UPL. It's the wrong folder. Yeah, I got renamed in the meantime. Okay, so that's the UPLC, and this is all. So that's the good answer for what it means to have a prepacked Fibonacci. This is the byte-string literal. So the whole program is in the byte-string literal, and the rest is there. And that was the UPLC code, and then the source code here. This is the reference to the source code repository. Let me click it. And that's how you do the prepackaging. So people can learn from that. New developers can come and see, oh, I need to use this strategy. This is like how you do this. We can also, if we are good on time, I don't know, how much time do I have left?
Until 3:10.
No, the next one starts at 3:10, so we have to turn the room around. The next
No, next one starts at 3:20. So you have, like, you can wrap up in 5
Yeah.
minutes. So.
Yeah, so let's wrap up by looking then at this thing. By the way, do you see it? Is it big enough?
Yeah.
Okay. So this is the table. If we go to, and I've noticed that Plutarch and Aiken, even though they use the prepackaging strategy, they use it differently. So they prepack. So the Aiken would use a varlang encoding when prepacking, and Plutarch would use fixed lang encoding. So 3 bytes per result. And I guess there is another like a trade-off maybe on top of already like a good set of trade-offs.
The rule of thumb is executing UPLC, anything on UPLC other than constant is expensive. So avoid evaluating anything.
The second best solution for this is the tail recursion one. And
Yes.
that one is a huge showcase of why metaprogramming is so good for this. Because the solution that KTOR's posted, I did like some light metaprogramming over it, and it was like 80% more efficient.
Yeah,
So I like looping.
let's take a look. This is the Aiken tail recursive Fibonacci, right? So the source code, and Aiken embedded their source code, so it should be all there. It's an Aiken project. Fibonacci. That's it. So, yeah, we can see it's not naive recursion, but it's still recursion, and it's way better. So second best, right?
You add some if statements that just check, oh, if it's greater than 5, then you do all 5 at once.
Mm-hmm.
Then, yeah, just it becomes like 80% more efficient after one if statement. Instead of doing recursion, doing the computation once per recursion.
Sorry, what's
So right now it's doing that addition. Every time it's recursing, it's doing that addition. And this is super expensive in on-chain code, right? So we have Fibonacci, right? It's going to recurse, it's going to do addition, add tail recursion, etc. But not this one, the tail recursion one. But
Yeah.
How you do it optimally is you do, okay, if n is greater than 5, right? We have 5 more steps to go. We're just going to add all 5 in this step of recursion.
Okay.
And then it makes it so per time you're recursing, you're doing 5. So if you have 25, you're only recursing 5 times. And the cost of recursion in UPLC is insanely high. So
That's something to think about. Just to me, it's crazy that first of all, recursion is not a primitive, and that it's so expensive. It's insane. And everybody, essentially to speed up, or make it cheaper, not speed up, make it cheaper. Everybody just unrolls.
It's like crazy.
Insane.
Yeah.
Yeah, tomorrow I'm going to show off the most disgusting production code you'll ever see. Just like pages and pages of just simple utility functions.
The time flies. Thank you.